some work is this Riemann bilinear relation. So this is a properly general form. So it says that any complex polarized abelian variety with polarization of type, I'll say in a second what I mean by this d1, dg. So these things are integers, each dividing the next one. And principal polarization means this is a bunch of ones. Okay? And the way you get these integers is if you look at the 2 form given by the polarization. You know, a polarization is an ample line bundle. It's an element of H11. So it's a quadratic form, symmetric, anti-symmetric, you know, depending on how you rotate things. And these are just the diagonal entries in the diagonalization of this form. Okay, so the form you should think of as diagonalized like that. And then if you have a polarization of type d1, dg, then any complex polarized abelian variety with this type of polarization can be written in this form. You can always choose the first g vectors to be the generators as the basis vectors of CG, and then the remaining g vectors will be a matrix tau, which will be positive definite, but this is the correct condition. So tau times d is d times tau. So this there should be some transpose, which of course I forgot to write here. Maybe here, doesn't matter where you write it. Okay, sorry, thank you. So last time I somehow didn't write d and didn't write principally here. So I should have done one of the two things. I could have either written any complex principally polarized abelian variety, and then that's what I said, or I could have written this thing. And of course this was confusing because then somebody asked whether any complex polarized abelian variety is automatically principally polarized, and it's not. It's isogenous to one. So any abelian variety, the word complex here does not play such a role. Any polarized abelian variety is isogenous, which means it meets a finite map onto a principally polarized abelian variety. Okay. So this is just to make sure that what I said wrongly last time is now unsaid and said correctly. Okay? I still have not given you a proof, and I will not. Okay? So hopefully this clears up some confusion that some kind person has brought to my attention since. Okay? So the goal, we have 3 more lectures. So today I'll try to talk about compactifying things, and things will mean moduli of hypoelliptic curves, moduli of curves. You know how to compactify. I will mention this a bit. And moduli of abelian varieties. And then we'll have 2 more lectures on Friday, and hopefully after the festive dinner on Thursday you'll be well rested, and we'll do the heavy lifting. So we'll compute the canonical classes of the moduli spaces, and then I'll prove that some moduli spaces are of general type under some assumptions, and how many of those we will prove to be of general type depends on how fast we go, so I don't know. Okay? So today again there will be no theorems, I'm sorry. The theorems will come next. I'll try to describe for you, not define, unfortunately, compactifications of the moduli space of abelian varieties. I would be delighted to define them, and I would be happy to come back and spend a good 5-10 lectures defining them. But that's about how long it actually takes. Okay, so we won't do that. So let's get to it. So today we'll be compactifying, and this is our topic for today. And what will we compactify? Well, we have 3 spaces, hypoelliptic curves, and abelian varieties. And I'll allow myself to write this as included each in the next one. This is a Torelli map, and the hypoelliptic curve in particular is a curve. Okay? And last week, Edoardo Cernesi described compactification of MG. Melody this morning did a lot with dual graphs. I'll do less. So let's first look at the hypoelliptic curves. And let me try to describe how to compactify them. Some of this, admittedly, and for a good reason, will be a repetition, in my own words, of what you know. But then we'll do something else which will also lead you to think about other things. I'm doing this not because we need it, but because it's nice, and it's right here, and it will help you maybe think about degenerations in a different way. So let's compactify this guy. So what did we discuss? We discussed that if I think about the hypoelliptic curves, this is more or less the same as the moduli space of curves of genus 0 with 2g plus 2 marked points up to the action of the symmetric group S2g plus 2. right? Because you can write a hyperelliptic curve as y squared as a polynomial of degree 2g plus 2. These are your 2g plus 2 points, and that's it. Okay? Maybe you should take this equality with a grain of salt, especially if you like orbifolds, but this is more or less true. So let's think about it this way. So if I want to compactify the moduli of hyperelliptic curves, I can compactify this. So how to compactify this? This will be our first attempt. And you know how to do this. So I should put a bar here. This will be the Deligne-Mumford compactification. And you had your GIT class that I hope covered this, right? So what is this? This is 2g plus 2 points up to PGL2 GIT quotient. Okay? GIT compactification. So this means that you should allow the points to come together. So allow points to come together. And just so that I bring back what has been going on here, let's do a couple examples and then I'll stop, I promise. So let's look at M04 bar. So this means I want to compactify. Yes, we all know the answer, but I want to look at it in a different way. So these are 4 points on P1. And why is the space not compact? Because I'm not allowing the points to come together, right? So I should allow the points to come together. So what could happen? So I have a P1, which of course I'll draw like this. And I have points, and there are 4 points, and they look like this. And maybe these two guys are trying to come together. Okay? So then I should tell you what is the limit in such a family. And the limit in such a family is that you keep the P1. There is this one bad point where these two guys came together. And I should draw a P1 at this place and put the 2 points. So the limit is equal to this. Okay? So this is a picture of two P1s. And if these points are 1 and 2, these are points 1 and 2, and these are points 3 and 4, and they didn't go anywhere. Okay? You notice one remarkable thing here. If I look at this picture, and I forgot that there was a family and point 1 was tending to point 2, if I just look at this, it looks completely symmetric with respect to replacing 1, 2 by 3, 4. While you would expect that here I can make point 3 tend to point 4. And of course, it would break off at a different point, but you know, these are two P1s with 3 points, so we have no moduli, right? So this somehow tells me that latent point 1 tend to point 2 and latent points 3 tend to point 4 are exactly the same thing. Which is true, because if you think about this, think these guys have some coordinates. So suppose points 1 and 2 are getting together. But let me just preclude them from doing them. Let me, you know, they get together by a factor of 2. I'll rescale my coordinate on P1 by a factor of 2. They'll stay at the same place. But then if I'm rescaling the coordinates so that these guys don't go anywhere, this effectively means I'm shrinking those two. Right? So suppose these points are 0 and 1 and something and something. And then this 1 decided to become a 1/2. If I rescale by a factor of 2, this is an automorphism of P1, this will be points 0 and 1, but these 2 points will be multiplied by a factor of 2. So if I keep rescaling, they will go off to infinity together. So this tells you that somehow letting these 2 points coalesce is the same as letting these 2 points coalesce. And this method of thinking will tell you more. So you can ask here, should we let 3 points come together? Because in principle, you should worry that maybe you should, right? There are 4 points on P1. Yes, I have described the generations when 2 points come together. What about 3 points come together? So the answer is no. We can always rescale. By rescale, I mean apply gamma in PSL to C such that these 3 points stay fixed in a family and the 4th points does not approach them. which should not be surprising for you because we have already described this. You know that I have fixed 3 points and then the fourth point just varies, and all it can do is can hit one of these 3 points. These 3 points are not hitting each other anymore. So this was M04. This is example 1. Let's do example 2, M05 bar. Okay, so now I have 5 points. Of course, if 2 points hit each other, I should allow things that look like this. Right? And this is, let's say, 1, 2, 3, 4. And this is the limit in a family where P1 approaches P2 and everything else stays fixed. Okay? But then again, if you look at this picture, this also looks like the limit in the family when these 3 points come together. So that would seem to indicate that we should not let 3 points come together. This is very good. So this is the boundary. So what I just told you here was that the boundary of M05 is, well, a number of copies of M03 times M04. Why is there a number of copies? Because when I write M05, there is point number 1 and it's different from point number 3. Okay? So that seems to be correct, except I should compactify further here and here. Compactifying here further does absolutely nothing. This is still a point. But compactifying here further is meaningful, right? M04 is non-compact. So this thing here includes a point that we have described a second ago. And so this means in the boundary of M05, I will also see a point that looks like this. Okay? And now we're done, because there is no further way to degenerate anything. Okay? So do all of these pictures make sense to all of you now? So this is a picture of a nodal stable curve consisting of 3 P1s. I didn't put the weights that Melody was putting because here everything is genus 0, so all the weights are 0. And this is where the points go. Okay? So this is how you can think of compactifying M0 to G plus 2. And then given such a picture, I should be thinking of this as compactifying the hypoelliptic locus in genus G. And what I'd like to describe quickly now is how to think of this in terms of hypoelliptic curves. Okay? Because this is another viewpoint on compactifying, and this usually goes under the name of admissible covers. Of course, I won't do admissible covers, as I don't do anything rigorously so far, but I'll try to give you some idea of what this means. So the question you can ask yourself is, what does this mean for compactifying the hypoelliptic locus? By which I mean, I know what the degenerations look like. What should I then think is the corresponding hypoelliptic curve? Because the hypoelliptic curve is used to be a double cover of P1 branched at these 4 points. So let's do M04 first. So here is my hypoelliptic locus in genus 1, also known as M1, and I know we've done this a ton of times, but never mind. Okay, so given 4 points on P1, I'm supposed to take a double cover branching at these 4 points. So let me draw it. There is a usual problem that our drawing skills, especially mine, are not so good in complex dimension 2. So these are smooth points. So this is a curve C, smooth points of C where the map branches. Okay? Maybe it's better to draw them like this, but this is also confusing, so it's your choice. So when I draw this, I mean that this is a 2-to-1 map from C to P1, which has 4 branch points, and that's my way to draw this picture. Okay? Okay? So now I'd like to know how this degenerates. So M04 degenerates in a very simple way. There is just one boundary point. And that's what the boundary point looks like, right? And before I had a double cover of P1. Now what happened was that my P1 broke into two P1s, right? So this is a P1, and this is another P1, which is somehow a new P1. And I don't really know which one is new, which one is old. I mean, they look exactly the same to me. And the curve C that sits above here should still be a double cover of this. So I can start drawing it. I'll start drawing. It's a double cover. It branches at this point. Branches at this point. It's a double cover on this side also. So it branches here, and now I come to the node. And I have to decide what on earth am I going to draw at the node, right? And this requires some thought. So locally near the node, I have a double cover on this side and a double cover on that side. And they don't branch. They look perfectly good. So I should just make them intersect. And these are nodes, even though they look exactly the same in my picture. Node. Okay? So this, I drew this in a very naive way, right? But you can make this formal. So if you formally and rigorously keep track of what happens under degeneration in the family, you can write a one-parameter family here. You write a corresponding one-parameter family of polynomials. You can see what happens. You will recover this picture. Let's try to understand what the geometry here is. Is this picture still visible, or is it not good enough? So there are two P1s. Each of them has a degree 2 cover branched at 2 points. And these two things intersect in 2 points. So there are two nodes. Okay? These are smooth points. This is just to indicate that the maps branch. So let's understand, this is a very weird way to draw a curve. We have not been drawing curves like that. I just want to emphasize it's a cover. So let's think what it is. So what are these components? So let's look at one component. So I have a double cover of P1 branched in 2 points, right? So on one of the P1s, so there is other P1 elsewhere. So here I have a double cover. Let's draw so that looks smoother maybe. So this is a double cover of P1 branched at 2 points. So what is the genus of a double cover of P1 branched at 2 points? 0. There is a wonderful map of a complex sphere, z goes to z squared, which branches precisely at 0 and infinity. So this guy here is also a P1, in fact. Okay? So if I now try to compact it to understand this picture, it looks like two P1s glued. Right? So this is a P1, this is a P1. Okay? At this point, of course, you should start objecting. This does not look stable. Okay? And indeed, as a curve, it's not a stable curve. But this, together with the data of a map, is a perfectly good object. And this is the kind of object you should allow in the boundary, if you're doing it this way. Okay? Let's do it a bit more general. Let's look at the covers here. So hopefully by now it's rather clear what happens. So this is a possible degeneration. So here I have a smooth thing. Here I have a smooth thing.
No, but you have 5 points.
I was going to get in trouble soon, and I want to get in trouble together with the audience. So let's wait. So let me try. So I'll try to do the same thing, right? So I try to do the same thing, right? It looks good so far. I have done exactly the same as before. There is a 2-to-1 cover here. There is a 2-to-1 cover here. There is a 2-to-1 cover here. It's very tempting to just go here and draw this picture, which corresponds to two nodes, right? Very tempting. And to do the same on the other side. Okay? Looks good. Looks like I've done everything very well. However, let's look at this component. Over here, over this component, over this P1, what do we have? We have a P1, and then we have a double cover of P1 branching at 1 point. What's the genus of a double cover of P1 branching in one point? Well, if you apply Riemann-Hurwitz, you get some unsatisfactory answer. It will be half integer. I'm unaware of compact Riemann surfaces of half integral genus, so this is not a good idea. Okay? So somehow by trying to do this, I got in trouble. And I have to save myself, right? So what should I do? Well, I should somehow create an extra branch point somewhere. Probably I should not create an extra branch point here at a random point of this P1. It makes no sense. So I should rather create a branch point here. Okay? And now, let's try to count whether we have solved our problem. So here I'm okay. On this side, what happened? Now I have a double cover of P1 branching at 3 points. The genus is also not very good. Okay, so I'm in trouble. So let's try to instead understand the picture more conceptually and correctly. So the reason I got in trouble was somehow I tried to solve the hard problem first without solving the easy problem. And I somehow started to understand the boundary of the hypoelliptic locus over this. And this is codimension 2. There are 2 nodes, so there are 2 degenerations. So this is a codimension 2 locus in M05 bar. And I shouldn't go straight there. I should first look at the double cover over this picture. 1, 2, 3, right? Because that thing here is a further degeneration of this. So I should just do it one step at a time. So let's understand what a double cover here should look like. So here, I certainly must branch. Here, I must branch. And now what do I do here? So it seems I have 2 choices. I can either just say that I'll glue these 2 things as nodes. This doesn't work so well, because in this case, on this side, I have a double cover of P1 which branches at 3 points. I could try to branch like this, in which case on the right, I have a double cover of P1 branching at 4 points, and I'm happy. On the left, I'll have a double cover of P1 branching at 3 points, which is also not good. Okay, so what can we do?
Sorry, why are you studying M05 to parameterize hyperelliptic curves?
Good question. This is why we are in trouble. This does not work. So you cannot do anything. So this tells you something. This tells you that this theory of admissible covers works under some situations, right? So let me now say what I mean by an admissible cover. Definition. A map C to E, C prime of stable curves is called an admissible cover. Oops. And let me only do double admissible covers. You can imagine that this can be generalized. Is a double admissible cover if over the smooth locus of C prime, it is a branched double cover. And for any node Q and C prime, and let's call this map pi, either pi inverse of Q is 2 nodes of C interchanged by the involution with the cover locally trivial at every node, at each, with the cover locally trivial at each, or the preimage of Q is one node and two local branches of C at this preimage map down to two local branches of C prime at Q by branch covers. Okay, this was a very long way to write a very simple thing. What is a double cover? It's a an admissible double cover. It's a double cover with a smooth locus, branching possibly, and here I allow either this map, where this maps like this. So this is to say that locally, over a node, I have two copies of the node. Maybe this guy is connected somewhere else, but locally at the node, I have two copies of the node, and each neighborhood of each of these two nodes maps by an isomorphism downstairs, or I have a node downstairs, and upstairs I have this picture, where these are two curves now. This is a node, and if I call these two components, this is local C1, C2, and this C1 prime, C2, then Ci to Ci prime branches at Q. Okay? So that's what an admissible double cover is. What did I exclude? I exclude the possibility that there is a node here such that the double cover interchanges, the involution of the double cover interchanges the two components. That's what I really excluded. Okay, so this is the definition of an admissible double cover, and this allows us to compactify the hypoelliptic locus. And the problem here is that nowhere in this definition there is any guarantee that such things exist. So the computation we previously did shows that if I want to have double covers of two P1s branched in such collection of points, they just don't exist. Luckily for us, if the number of points is even, this works. So let me try to say what I'd like to see from this discussion here. So proposition, boundary divisors of M0 2G plus 2 over SG plus 2 are all of the form M0I plus 1 times M0 2G plus 2 minus I plus 1, where I must be at least 2 points go away, and at most, whatever. Okay? So this is something that was present in some guys, or maybe in very similar guys, in Melody's talk. I just quotiented it out by the symmetric group 2G plus 2 to make sure that I don't have to label the points, I just have to say how many go where. So what is a boundary divisor here? It's a curve that has two components, has one node. And since these are both of genus G, all I have to, genus 0, all I have to tell you is where the points are. And the points are all created equal, so I only have to tell you how many points are here and how many points are here. Okay? So these are the boundary divisors here, and then it follows that boundary divisors of the hypoelliptic locus are of the form, are admissible covers of the following form. So downstairs I have this, and there is I here and 2g plus 2 minus I here. And here I either have a cover that branches, and then there are two nodes, and then branches on this side. And this is possible if I is even, or the same picture and then if I is odd. And if I now were to interpret these pictures not as double covers but as hypoelliptic curves, so these are two hypoelliptic curves intersecting in a pair of points interchanged by the involution. Okay, and these are two hypoelliptic curves intersecting in Weierstrass points. Okay. Weierstrass point is a fancy name for a branch point of the map to P1, and this is your possibilities. What have we learned? We have learned, well, nothing particularly useful maybe, but we have learned that the boundary of the hypoelliptic locus has this set of divisors, which we have described explicitly, and they all are described as hypoelliptic curves of genus smaller with marked points, similarly to MG. So this is a compactification of the hypoelliptic locus, and you can see that the Picard group of the compactification of the hypoelliptic locus is generated by the boundary. Because the hypoelliptic locus M0, 2G plus 2 are affine, so there are no classes in the interior. So exercise. Compute the canonical class of the hyperelliptic locus. Okay. I will not do this because for the hyperelliptic locus, whatever the canonical class is, it's some kind of linear combination of these guys with some coefficients that you can figure out by following through this method very carefully. But I know that the Kadairy dimension is certainly minus infinity. I don't have to worry. Okay. Has Kadairy dimension been defined? No. Okay. I'll define it maybe next time and discuss it for a bit next time. But I want to say here that you can compute very explicitly from these considerations the canonical class of the hypoelliptic locus by hand. This will not be the case for the canonical classes of mg bar and ag bar, and that's where we are going. You won't be able to do this by hand. You'll need to use some machinery, and that I'll do Friday morning. Okay, but now let's move on. Questions?
Sorry, I
Yeah.
didn't understand which kind of covering we are getting rid of.
So in this definition, I said nothing, but instead of thinking of a cover, you can think of a curve with an involution of degree 2, right? With an involution, right? And if you have a node, there are two branches of the node, and your involution can do various things. One thing it can do is it can fix the node and interchange the two branches. This does not happen. Okay? So here, the involution interchanges two nodes, and then that's it, right? I mean, whatever I wrote about locally trivial, I mean, follows from the fact that it interchanges two nodes, just to explain what it is. So you can... yeah. Here, the involution fixes each of the two local components and just makes it a double branched cover of something downstairs. So this component locally is a double cover of this component locally, and this component locally is a double cover of this component locally. Okay? But in principle, you could have a node with two components interchanged, and then locally down below, this will be a smooth point, and that's not allowed. Okay? Okay. So I don't want to say the word hypoelliptic locus ever again in this course. Any questions on hypoelliptic locus? So the reason I did this is it's extremely explicit. You can do everything by hand, except that the moment you start doing anything combinatorial, you start suffering. For the hypoelliptic locus, not so much. As Melody mentioned, if I don't quotient out by the group action, the combinatorics of the boundary divisors gets extremely hard. For the hypoelliptic locus, it doesn't get quite as hard, but still hard. But somehow these easy co-dimension 1 geometric questions are very explicitly doable. Okay? And this is also a way to tell you what admissible covers look like. You can generalize this. This does not give you a way to compactify MG, because if I have a higher degree cover, maybe there are simple branch points that cease to become simple. All sorts of bad things can happen. For a double cover, every branch point is a simple branch point. For a triple cover, you can have a triple branch point, where all three branches come together, or the double one, and one can degenerate to the other, and this becomes a mess. Okay? And you don't have a map to P1 given, so you have to worry about this. Okay.
There is no problem that the curves that you get are no longer stable, not necessarily stable.
They are stable.
You show us an example in genus 1.
Yes. In genus 1, the problem was I was trying to compactify M1, and it was unstable to start with. Right? So the space M1, as far as I'm concerned, does not exist. Right? I mean, it's an Artin stack if you wish, but it doesn't exist. So M11 is good. Okay? If I want to think about hypoelliptic curves, I mean, I'm not even sure this is M11 and not M12. Maybe I should label a pair of conjugate points or something like that. So whatever I did in genus 1 is okay. I mean, it's as unstable as just an elliptic curve is. So it's not so bad. In height...
So if you further degenerate and you get one P1 with 2 points and then no branching in the nodes, you're going to have the same problem, right?
I hope there will be an exercise session. This can be discussed. So, I mean, this is a correct description, right? What I said is correct. You have to read it to understand what this should be, right? Correctly. You see, the stability for an admissible cover should be a different notion than stability for a curve principle. And the map goes somewhere down, and I'm trying to just say, let's not worry about this. I don't have the right to do so, but that's what we do. Okay. So I won't say anything about compactifying MG because you've seen this done. It draws the same kind of pictures, graphs. Now they are not trees anymore. They're more complicated. You forget all the admissible cover business. But you know how this is done, and I won't have anything to say about this at the moment. I'd like now to try to explain to you how one can compactify the moduli space of abelian varieties. And I won't be able to do this, so I'll only give some motivation now, and then I'll tell you something about what the result looks like. I won't be able to define this result. So for motivation, recall that there is this Jacobian map, the Torelli map, that sends mg to ag. And I would really love to be able to extend this to compactification. So we want something that looks like this. Okay? And this should guide me maybe in how I define a compactification. This is the wrong motivation, but it's instrumental in defining the first step. So this means I should be able to understand what I should declare the Jacobian of a stable curve to be. So let's look at the boundary divisors here. There is a boundary divisor that looks like this. So this is a curve of genus I. This is a curve of genus G minus I. Let's call this curve C1. Let's call this curve C2. And there is a point Q1 identified to Q2, which is the node. Okay? This is a generic point of one of the irreducible components of the boundary of mg bar. Is this okay? The number of nodes is the codimension of a stratum in the boundary. There is only one node, so it's a codimension one stratum. This is a possibility when I have labeled the genera. Okay? The dual graph has two components, one edge, I, G minus I. Okay? So what should the Jacobian of such a thing be? You can just check this from the analytic definition explicitly. And maybe you feel uncomfortable with PCARs for singular things, which is fine, you maybe should. But from the analytic definition, I should just be able to see this. So basis of, H naught of holomorphic differentials are holomorphic differentials on this thing, on C, are holomorphic differentials on C1 plus holomorphic differentials on C2. And there are I of them here, and there are G minus I of them here. And this definitely should be holomorphic differentials on the total space. And then if I want to compute the period matrix, well, if I integrate the differentials here on cycles contained in here, I get the period matrix of C2. So maybe what I'm doing actually is computing the period matrix. The Jacobian will come in a second. So the period matrix continues to be denoted tau. And this will be the period matrix of C1, 0, 0, period matrix of C2. If I need to choose a basis for holomorphic differentials on this guy. Of course, I should be saying the word relative dualizing sheaf in a second. But you can see if you do a very simple degeneration argument, open up this node, that the holomorphic differentials on C2 extended by 0 to C1 and holomorphic differentials on C1 extended by 0 to C2 are holomorphic differentials sections of the relative dualizing sheaf on C. If this is the case, I can compute the period matrix. So my cycles will be A1 through B to I, BI will lie here, and A G minus I plus 1 through BG will be here. Right? Remember last time we were choosing the basis for homology, and homology of this is the sum of the two homologies on the two sides. Two curves intersect on a point. Any path lies either in one or the other, or is the sum of the two. And then when I integrate holomorphic differentials that are non-zero here over cycles here, I get the period matrix of C1. If I try to integrate a holomorphic differential here on a cycle in the other direction, this is 0, and vice versa. Okay. So as a consequence, we see that the Jacobian of this guy, C1, C2, is the product of the two Jacobians. If you have an abelian variety and another abelian variety, their product is also an abelian variety. And this is what this is. This somehow is both good news and bad news. The good news is I didn't have to try to compactify the modular space of abelian varieties to extend the Torelli map here. The bad news is this map used to be injective on the open set, MG. This is no longer injective. Why is this no longer injective? Because it forgets the marked points. Okay. This Jacobian does not depend on where I have attached my two curves. So the injectivity of Torelli theorem immediately fails if I go to such a stable curve. But the Jacobian of such a curve is a nice principally polarized abelian variety, which happens to be a product. That did not help me to compactify AG bar, to compactify AG. Well, what is the other useful trick to do? There is another divisor that we have not considered yet. So this is the divisor of irreducible stable curves. So I have a curve C of genus G minus 1. The dual graph would have one vertex of weight G minus 1 and the loop. And now I'd like to understand what is the period matrix of this thing. Okay. So my notation will be C will be the nodal curve, and C twiddle will be its normalization. The word normalization is just to say that we disconnect Q1 and Q2. Okay. The genus of the normalization is G minus 1. That's what I wrote here. That's what I meant anyway. And if I choose a basis of sections of the relative dualizing sheaf, so this is what the canonical bundle becomes at the boundary. Has it appeared? Did Eduardo do this? Eduardo must have done it if he described MG bar. Okay. If you don't know what I just wrote, the statement is, i.e., the limits of a basis of H node CT KCT as CT degenerates to T to C. Okay, that's what I mean. And you can do this completely complex analytically without saying the fancy word relative dualizing sheaf if you want. Is the following: omega 1 through omega G minus 1, which are a basis for the sections of the canonical bundle on the normalization. The normalization is a smooth curve of genus G minus 1. If I have a smooth differential holomorphic one form there, this clearly should be considered as a smooth one form here. Okay. Now the actual definition of the relative dualizing sheaf, if you remember that, tells you what the other guy will be. And some differential, let's call it capital omega, which if I think of it as a differential on C, twiddle on the normalization, it has simple poles at Q1 and Q2. So this is, in simple terms, meromorphic one form on omega with, on C twiddle with simple poles at Q1, Q2. Okay? Our goal is to try to compute the period matrix. So if we want to try to compute the period matrix, let's try to understand this degeneration. So how do we degenerate? So, question? Let me draw the complex analytic picture, not this picture. So I start with a curve. Here is my curve, which has some interesting geometry and whatnot. And then it has a hole here that I'll concentrate on. And then I start pinching here. So I pinch. Which color is visible? Orange, red, something? So I pinch this. Okay? So if I start pinching, what this means is that my Riemann surface stays the same elsewhere, but then here, this thing becomes thinner and thinner. So this is now a very thin thing. And in the limit, once I have pinched, this has become a node. Yeah? And now I should be able to tell you what happens to the basis of cycles. So what are the cycles? So I have cycles here and here. This is AI and BI. They don't go anywhere, right? These cycles did not feel the fact that I pinched. However, there is this cycle here. Let's call it AG. Let's call this BG, sorry. And there is this cycle around here, which is AG. In the limit, I can still see the cycle BG, this cycle. So, and the limit of AG is the node. It's just one point. I have taken a curve and I have pinched it to one point, a node. This is what happened. And now I would really like to be able to try to understand what this means for the period matrix. So if I take some omega I and I integrate it over bj, and this is still okay. So these are periods of the normalization, obviously. This thing just lives entirely on the normalization seat twiddle. Okay? The integral of omega I over AG was always 0 as we were deforming the family, so it stays 0. So the integral over AG tends to actually computing the residue, well, 2 pi I times the residue at the node, which tells you that the integral over AG of omega g tends to the integral over AG of this one form, which I can normalize to be 1 of residue 1. Okay. So this implies that omega 1, omega g minus 1, omega is a limit of normalized basis of differentials. Okay. So I have sort of proven this statement, if you think about it. So what I said is I can choose these differentials in such a way that this guy here has residues here and 0 A periods. And then this G tuple of differentials, these guys, and this dipole differential that has 2 poles, are a limit of differentials on smooth Riemann surfaces in the degenerating family. So if I want to compute the period matrix, what remains to compute are the integrals over bg of omega I, and more interestingly, the integral over bg of omega. Okay? So the period matrix has the following form. So period matrix of the curve C, it has a g minus 1 by g minus 1 block, which contains the integrals of omega I over bj, and this is just the period matrix of the normalization. Then there is one entry here and one entry here, and here I'm supposed to write the integral over bg of omega I, and here I'm supposed to write the integral over bg of omega I, which are the same, and here I'm supposed to write the integral over bg of omega, right? The period matrix are the integrals over the b cycles of a basis of holomorphic one forms. Here I get the period matrix of the normalization, which I'm very happy with. Here I get this integral. So this is the integral over this thing here, and it looks like the integral from 0 to infinity of dz over z, right? Because locally near this point, the form omega looks like dz over z. And this is what I'm integrating. Twice, maybe this, okay? This is clearly infinite. Moreover, if you work it out correctly, there is an I infinity. So this is I infinity. This is bad news, right? Infinity is not a number I can really deal with in a meaningful way, but this is what it tells us. Now, what are these things here? The integrals over bg of omega I. If I draw the curve, which is a normalization, there are points q1 and q2. This is a normalization. The curve can be mapped by the so-called Abel map, Abel-Jacobi map, to its Jacobian by taking a point P to the set of integrals of omega I up to point P from some other point. And this is then nothing but the Abel-Jacobi map of Q1 minus the Abel-Jacobi map of Q2. Okay, we suffered long and hard, and there must be a reason, and we have about 2 minutes, which means I'll go another 2 minutes over time, sorry, to explain what the reason was. Okay, so what have we done? We have computed, quite honestly, the period matrix of such a degenerate nodal curve. And we have discovered that it has the following shape. It has tau of the normalization here, I infinity here, the Abel-Jacobi map of Q1 minus Q2 here, the Abel-Jacobi map of Q1 minus Q2 here. Maybe I should put a transpose to indicate one as a vector, one as a covector. So this is what I have. I would write, yeah, good. So this is the period matrix of C. And I don't really have any choice. I mean, this is what is naturally appearing here. So however I compactify AG bar, if I want the Tarelli map to extend, I should allow such things. And infinity is not so good. The infinity is not so good because if I take C to the G, quotient Z to the G, plus such a period matrix, Z to the G, this is not compact. Because I have an infinity. I'm not gluing points. There is one infinite direction. Okay? So definition. A semi-abelian variety of torus rank 1 is the following thing. Semi-abelian variety, let's call it G, is a group such that it's an extension of an abelian variety by a C star. Okay? And that's what this quotient really is. This quotient is an extension of my case of the abelian variety. It's abelian variety. Yeah? This thing is a C star extension of that. The C star corresponds to this extra dimension. Because if you think about this extra dimension, if I suppose this A is not there, then this would be just a product of C star, because if I take C quotient by Z, this is C star, right? If I write in a very silly way Z plus infinity Z, this does not change anything, right? This is a C star. So if this were 0, this would be a product of C star and an abelian variety. In general, it's a non-trivial extension. Okay? This is not compact. A semi-abelic, notice the difference, variety of torus rank 1 is a completion of this to a P1 bundle over A with 0 and infinity sections identified via a shift by this point. Okay. So if I just take the naive period matrix and take the quotient, I get a non-compact thing. So now I would like to make it compact. So C star is not compact. I would like to add 0, but there is always the issue of the involution, which interchanges 0 and infinity. So I better add both 0 and infinity to C star, but then I have to declare that they're the same. Because if you're thinking about how you compactify this quotient, 0 and infinity are really the same here. And so this means I should glue the 0 section of the P1 bundle over A to the infinity section of the P1 bundle over A with a shift. And this is the definition. Okay. So I should stop now. And this is not the end of the story. So far, this is actually rigorous, what I did. So far, it didn't look that way because I didn't have enough time. But so far, we have rigorously computed period matrices of Jacobians of codimension of this sort. And we have ensured that they are indeed semi-abelic varieties in this sense. Alternatively, you can do this by talking about torsion-free sheaves. But this would be a completely different story and wouldn't give you this explicit construction immediately. Okay? And I wanted to do it fast. This has not yet compactified AG bar because I have only gone to these curves, and you can now draw something like that and ask me what the Jacobian of this will be. Okay? So I'll make some comments next time as to how this works, and then I'll say that there exists a compactification such that the Rayleigh map extends, and I'll list a bunch of properties of this compactification that we'll use that you'll have to trust me on, and then we'll move on. Okay. That's it. Sorry I'm over time. Thank you.